Good morning and welcome to AP Statistics. Today we're going to go over the homework assignment that was posted for page 101, numbers 13 through 16. And just to give a brief review of the material covered yesterday, which began chapter 2, which was location in a distribution. So let's get to that. I'll just pick this up. Number 13 gave you a story about bone density. Obviously, it's good to have the appropriate bone density. You don't want your bones to be brittle. You don't want them to be unusually dense. We have a story here about Judy, who is 25 years old. Her bone density measured using the DEXA. Her results indicate a bone density in the hip of 948 grams per square centimeter, standardized Z-score of negative 1.45. In the reference population of 25-year-old women like Judy, the mean bone density is 956. So it says, part A, Judy hasn't taken a stat class in a few years. Explain to her in simple language what it means, the standardized score. Negative 1.45 is basically telling us that Judy's bone density is lower than typical for her age group. Specifically, she's 1.45 standard deviations below the mean bone density score, which in her case might be a bad thing. It might indicate osteoporosis or some other issues. Okay, part B. Use the information provided to calculate the standard deviation of bone density. They gave you what you needed, so if you wanted to put that on paper here, we got her Z-score was negative 1.45. I'll start off by just recapping the Z-score formula. The Z-score is equal to a data point minus the mean divided by the standard deviation. So we know her Z-score is negative 1.45. Her score was 948, and 956 is the average. So it's got to be something we saw for sigma. So subtract the numerator, multiply by sigma, divide by negative 1.45. It's just algebra, but you get 5.52, roughly, grams per square centimeter. Okay? Again, it's just algebra in that case. Once again, the Z-score tells you your position relative to others in your distribution. So for everyone who is 25 years old, female in her distribution, she was 1.45 standard deviations lower than the typical. Is it always bad to be lower than typical? No. Think about things like golf. Where do you want to be in a golf game? You want your total strokes to be lower than the average number. You win if you have fewest strokes. What about your cholesterol level? You don't really want to be very high with cholesterol level. So you want to be at 0, really, which is the appropriate level, or even a little negative. Because, again, there's different kinds of cholesterol. You want lower LDL and better HDL, doesn't matter. The point is, it's not always good to be high Z-score. You don't always want a Z-score that's positive, because sometimes it's best to be at 0 or even lower, depending upon the context. It always depends upon the context. Okay. Let's see, that was 13. 14, more bone density with our friend Mary now. She's 35, so they have a different mean. Her density is 948. Her standardized Z-score is 0.5, and mean bone density in her age range is 944. Whose bones are healthier, Judy's or Mary's? Relative to their age groups, Mary has better bone density. She's only slightly above the average bone density, which I think in general is better than low bone density, but also she's much closer to the average. So for her age group, and again, it's specific to the age group, Mary's bone health seems to be better than Judy's. All right? What else was there here? Calculate the standard deviation of bone density for Mary, and how does this compare with our answer? If you find the bone density for Mary's group the same way we found it prior, you get 8 grams per square centimeter as the standard deviation from Mary's age range. What it means is 8's bigger than 5.5. There's more variability in Mary's group. For 35-year-old women, the average distance to the mean score is actually larger than for the 25-year-old women group. Make sense? Okay. Let's see now. We had baseball salaries, number 15. It gave you a dot plot, which was very clearly, seriously right skewed. And it gave you the relative values beneath it. Brad Leach played a crucial role in the Phillies' closer, pitching the end of many games throughout the season. Salary for 08 was $6.35 million. All right, find the percentile corresponding to his salary, explain what it means. If you just count the dots that precede his score, you'll know what his percentile was, because again, it's just based upon where you fall in the pack. If we counted that up, let's see what we have. There were 22 salaries less than his. His salary is higher, therefore, than 22 of the 29 in the distribution, which was the 76th percentile. That's all you got to do for problems like this. It's not more complicated than that. You're just counting where his data point falls and what percent of the distribution he beat. There's your answer for part A. Part B, you want to know the z-score corresponding to his salary. Explain what it means. His z-score is his salary, $6.35 million, minus the typical salary, $3,388,617, over the standard deviation, which was $3,767,044. Where do those numbers come from? Well, they were given to you in the breakdown just below. It says mean, it says standard deviation. It's telling you what you need to know. And you get a z-score of this guy, 0.79. So his salary was 0.79 standard deviations above the typical salary for the team that year. Slightly above. Okay, and then what brings us down to the final question, more baseball salary. Did Ryan Madsen, who's paid $1.4 million, have a high salary or a low salary compared with the rest of the team? Justify your answer and then calculate z-score. We can see by the dot plot that the majority of the team was in the $0 to $2 million range. So having $1.4 million doesn't look like it's all that unusual. You see the mean was $3 million and change, but that's also because of the high values on the right side skewing the data. The median was $1.4 million. So this guy, Ryan, had actually the median salary, which says he's at the 50th percentile. That says right there that it's not unusual. But if we go and do the math that was suggested, let's see, Madsen's salary was $1.4 million. There were 14 salaries lower than his. Therefore, again, he's at the 48th percentile, which is, pretty much right in the middle. His z-score, if you calculate it, is negative 0.53. So he's like a half a standard deviation lower than the mean score. But again, that's also because the mean is affected heavily by the high values on the right side. He had a typical salary. That's really what it says. I mean, especially if you look at the median, which is listed there for us, it is his salary. So again, not unusual. His z-score was negative, indicating it was below the average. But again, that's clearly due to the very high outliers here. We have one person making over $14 million, one at 10, four of them in the $8 million range, three in the $6 million range. The point is, out of 29 team members, like 6 of them had salaries of $8 million or higher. Everyone else was in the lower range. So that's how we're reading the data to answer the questions. Real quick though. Yesterday's lesson had to do with z-score, obviously, and so did the homework. Linear transformations, I did not give you homework for, but it's covered yesterday. We had talked about what a linear equation, y equals mx plus b, could be looked at in statistics, y equals a plus bx, a being a constant shift and then b being a multiple shift. I told you what it had the effect on. The a, the constant, mostly has its effect on measures of center, mean, median, the quartiles 1 and 3. The high and the low value obviously will shift also, but the measures of spread were not affected by a constant shift. However, a B value, a multiple shift, affected everything, not just measures of center, but all the measures of spread as well, including standard deviation and IQR. Keep that in mind. What I want to look at real quick is just one more thing for this portion, and it's called an ogive, and I really, for the life of me right now, can't remember if we've ever looked at one before. But an ogive is called a cumulative relative frequency graph, and it shows us basically percentiles as a graphical image. An ogive will show you, remember the frequency distribution where each class ended at a certain level, how we made a histogram? Well, if you just graph the endpoints of each class and the relative frequency that has been accumulated, okay, I'll just adjust that there. So let's just say end of class 1, 2, 3, and 4, and 5. I'm not going to go crazy with it. At the end of each class, you have a certain relative frequency, which you remember from the histogram. If I add up the relative frequencies as we go, we are accumulating all that relative frequency. By the end of all the classes, we should have accumulated 100% of the relative frequencies because they're adding up. So if you have 20% in the first class, well, let's just say that goes over here. So I've got 20% of my relative frequency accounted for. In the second class, let's say there was 40% more. Well, that's accumulating now. So there was 20% already. 40% more is now 60% by the end of the second class. Let's say the third class didn't have much in it. It only had 10% more. So it's accumulated another 10%. So now it's at 70% by the end of the third class. Let's say the fourth class had nothing in it. It was empty. There was nobody in the fourth class. So we're still at 70%. By the end of the fourth class, still at 70%. Nothing has changed because it was empty. And then, I guess class is over. And then at the end of the fifth class, we would have seen a big jump because everyone else was in that fifth class. It was a big category. So by the end of the fifth class, everyone else is added in and we get up to 100%. It's a picture of what an ogive might look like. Now, ogives are connected dot to dot by straight lines. No curves here, it's just straight line segments, dot to dot. And the very first one connects down to the origin. An ogive only climbs because you're accumulating relative frequency. It cannot decrease, and it never connects back down to the origin or to the axis. It never falls. So, looking at the ogive we just put together, can you find the median? Well, the median is the 50% point. So if I look across at my ogive at that 50% point and take a look and see where that falls, here's the median. It falls in the 1 to 2 column. And let's just say, we want to put a number on it, 1.75 looks like the median. Just putting out numbers here, okay? What's the first quartile? Well, that's a 25% point. And again, if I go down to the ogive and see where it falls, first quartile, I'm going to call that, 1.1. It's just the value on the horizontal axis where the 25% point meets. So it says 1.1. That's not the number I want to draw. Try that again. 1.1. And I had 1.7 as the median. Now let's find the third quartile. So I'm going to go to the 75% point, go over to the ogive where it hits. Looks like 4.4. Again, just estimating. This is just a hand-drawn graph for an example. From this, I could also find the IQR, because the IQR is Q3 minus Q1. Well, Q3 was 4.4, and Q1 was 1.1. So I have a 3.3 IQR. The median we found to be about 1.7. You can find the 90th percentile by going to 0.9, or where that would be, scrolling across and going down. That's how ogives can be used to find positions within a distribution. It's actually kind of useful. Okay, so here's what I want you to do. I've attached to the Google Classroom worksheet today. It's actually, I think I gave you 2 worksheets. Don't do both right now. Just do the 2.1a, the first worksheet that you see there. It's not really a quiz, although it says quiz on top. All I want you to do is do the 2.1a worksheet to the best of your ability, and we will discuss later. Now, if you're watching the video in the morning, please note, Google Meets will be activated during our class time. So if you've done this and you have questions on it, come in during the meet and ask me. All right? I'm not really intending to teach the same unit during the meet. I'd like it if you could actually watch the video first and then ask me questions during the Google Meet if you have any. That's all for today. So get that work done and log in later if you want to ask questions. Otherwise, I will talk to you soon. Bye.